Hello, good morning all. In this lecture, we are going to continue with the linear algebra that we were doing in the previous lecture. Okay, so in the previous lecture, as you remember, that we were doing a little bit of linear algebra, and today I'm going to continue with the same. Uh, don't worry, sooner we are going to get into our mode of uh, like proper this thing quantum mechanics. Okay, don't worry about it. A few things that were left, I thought that I should not teach, but now I'm thinking that I should teach that also. See, a few things that were left in linear algebra, I thought they were of not that importance, but I think that is even if we study the group theory, something like that we are going to study. Okay, so it's better that we should take a look at those topics as well. Okay, so one of those topics is isomorphism. Okay, isomorphism. So let us start with that. Okay, let us start with isomorphism. Okay, so see, whenever we are studying anything like group theory, okay, for example ring theory, for example vector spaces, and these algebraic structures, okay, in general, uh, a term like homomorphism and isomorphism would always come. Okay, uh, what does homomorphism and why do we study isomorphism? As a physicist also, you should understand that if we want to develop a symmetry between two structures, okay, if we want to develop a symmetry between two structures, we would use something called as isomorphism. Okay, that is, if one structure is isomorphic to another structure, then you can say that they are more or less same, they are more or less symmetric to each other. This is like very naive or very vague sort of definition, but this is how we actually associate, like as a physicist, this is how we associate isomorphism to. Now, a very stricter definition in mathematics is that let T be a linear transformation from U to V, and this is a linear transformation, by the way. Again, I'm stating that at times you'll find me using linear operators, and at times you'll see me using linear transformation. Okay, they are one and the same thing. Don't worry about it. Okay, so if this linear transformation is 1 1, and if this linear transformation is onto, okay, and in mathematics these are known by injections and surjections. If the mapping is injective and if the mapping is surjective, then we say that this t that is defined is you can say bijective. Okay, this t is referred to as bijective. Okay, probably from standard 12th you know that how to develop one-oneness. So for example, if u1 and u2 belongs to u, with u1 not equals to u2, then t of u1 will never be equals to t of u2. Okay, and if t of u1 is equal to t of u2, then u1 has to be equal to u2. If t of u1 is equal to t of u2, this implies that u1 is equal to u2. Then we'll say that t is 1 1. Then we'll say that t is 1. And how do you identify that your mapping is onto? For that, let's say I'm saying that let t be a linear transformation from u to v, then the range of t must be equal to v. Then the range of t must be equal to v. And what was range of t? So range of t included all those is nothing but image of t under u. Image of t under u. It represents the image of t under u. That is, it represents tx for all x belongs to u. So you take all the values from u, you find the images. That set is called as a range set. If range set is equal to this v means here you will say it is a codomain. So if it is equal to v, then we'll say that this particular t is onto as well. Now, whenever you establish these kind of thing, then we'll say that my T is a bijective map. I'll say that my T is a bijective map. Is that clear? Now, one thing that you can think of is that if T from U to V is 1 1, then T from U to V is 1 1 if and only if kernel of T is equal to 0. How does that happen? So let us assume that T is 1 1. Let us assume that T is 1 1. If T is 1 1, let's say if U belongs to some kernel of T, U belongs to kernel of T, what does it imply? It implies that T of U should be equal to 0. T of U should be equal to 0. I told you what is kernel. Kernel contains all those elements for which your Tx is 0. Okay, and it is equals to what? Remember, I told you that if it is coming 0, then it can be 0. If it is T is a linear transformation, I told you that T of 0 happens to be 0. It implies what? It implies U should be equal to 0. So from one side it is proven, and now if you assume that U1 and U2, conversely, let us suppose that. So this is how we do in maths actually. Whenever you have this kind of thing, if and only if we take both the statement. First we assume that T is 1 1, and we have proven that kernel only contains this 0 element. Now if we take U1 U2 to be belonging to U, such that T of U1 is equals to T of U2, what does it imply? It implies that T of U1 minus T of U2 is equal to 0. Since T is a linear transformation, I can write this as T of U1 minus U2. And since linear transformation is there, remember T of 0 can only be 0. It implies what? It implies U1 minus U2 has to be equal to 0. It implies U1 equal to U2. It implies T is 1 1. So from both sides we have proven that if T is a 1 1 map, then kernel can contain only null element. Then this kernel T will only contain this. Is that clear? So if and only if kernel T is equal to singleton 0, then T is a 1 1 map. Is that clear? I hope it is clear. Now remember, in standard 12th you must have understood, you must have read that whenever your mapping is bijective, an inverse function can be defined. So bijectivity is the primary condition for invertibility, if you remember from your standard 12th. Okay, so remember, if bijectivity holds, then T inverse is defined. That is, inverse linear transformation is also defined. And remember, this happens to be a linear transformation. If T is a linear transformation, then T inverse is also a linear transformation. This I'm not going to prove, but remember, this is a linear transformation. In fact, T inverse is also 1 1 plus onto. So you don't need to prove anything. I'm just stating these two theorems. This is an important thing that you should write. That if T is defined as 1 1 and onto, and why are we doing all these things? Please do remember, whenever I'm going to start with group theory, there I'm going to illustrate isomorphism for physics people. Basically, how do we relate to physics? See, in physics, a lot is to do with symmetry. Let's say if there is a translation symmetry in a system, let's say there is a classical system and there is a translation symmetry, then we say that law of momentum will be conserved. Okay? So this is how we are going to say. If there is a isotropy of time, we say that energy is conserved, if you remember from your Lagrangian mechanics. So symmetry has a lot to do in physics. And in fact, one of the quotations says that it was the playgrounds of group theory where particle physics took the birth. So basically, one has to understand this thing. One has to understand the importance of symmetry, and this is how we are going to understand about symmetry. Oh, did I forget to? Okay, no. Okay, are there people somewhere? I don't know. There are people. I'm talking all alone. So this is one thing. Okay, this is one thing that you should remember. Now let us see what happens if T is 1 1. So what happens if T is 1 1? One of the most important thing that happens is that if T is defined from U to V, and this T is 1 1 and onto, this T is 1 1 and onto, then what do we say? We say that U and V are isomorphic to each other. U and V are isomorphic to each other. That is, we can say that U is isomorphic to V. This is how we denote. One of the most important thing that you can think from here is that whenever you say whenever you say that two structures are isomorphic, whenever you say that two structures are isomorphic, let's say U is isomorphic and V is isomorphic, what is one important, there are two important assertions that can follow. The first important assertion is with regards to basis. So let's say if T from U to V is an isomorphism. So I'll repeat one question that I did yesterday. So that's why actually I was getting confused that why I'm directly using that particular question. Okay, not an issue. I'll repeat it. So if T from U to V is an isomorphism, then what should I? Then suppose that there are let's say bases of U. Let's say E1, E2, E3, En form the basis of U. Then very strong statement, very important statement, please remember, then TE1, TE2, all these become all these are what are bases of V. Now this is an important property. See, if you see that there are two structures which are isomorphic, then if E1, E2, E3, En form the basis of U, you don't need to think about basis of V. If they're isomorphic, then TE1, TE2, TEN will be the you can say what you can say are bases in V. TE1, TE2, TEN are bases in V. This is what we say. I'm not going to prove this. Just understand this thing. What is heavy implication for this? The first implication that you can think is that if E1, E2, E3 dash 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 En spans U, basis means what? It should span U. Then TE1, TE2 dash 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 TEN spans V. It spans V. Further understand these two are linearly independent set of vectors. Understand, because they are bases, then they form linearly independent set of bases. Like basis contains what? Linearly independent vectors, right? So one of the most another important way of saying this is that an isomorphism, you can say that an isomorphism, that is, you can say a 1-1 and onto 1-1 and onto linear transformation maps any linearly independent set or not set, I can say subset of U to a linearly independent set of V. Okay, so this is one of the most important thing. Another important result that comes out from here is in particular for finite dimensional spaces. So if U and V are finite dimensional vector spaces over field F, then do remember that dimension and I'm writing it here, then U is isomorphic to V. Let's say U is isomorphic to V, then dimension of U is equal to dimension of V. These are some very important results that you should remember. These are very, very important results. Okay, we have seen that if E1, E2, E3, En are bases of V, U, and TE1, TE2, TEN are bases of V, then Te1, Te2, Ten are bases of V, provided U and V U is isomorphic to V. And one of the more important statement, you can say that I should think I can write also that if T is defined from I'm so sorry be a be a linear transformation. Let T be defined from U to be a linear transformation, and E1, E2, E3 dash 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 En, this is a basis of U. This is a basis of U. Then T is 1-1 and on to if and only if TE1, TE2 dash 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 TEN is linearly independent. So if in case this is not linearly independent, this set does not appear to be linear independent, then T cannot be 1, 1 and on 2. This is very, very powerful statement. Okay. So one thing that I already told you, that if if T is an isomorphism, that is, it is a 1, 1 and onto linear transformation, then E1, E2, E3, En will get mapped to Te1, Te2, Ten. Fine. So if these are the bases of U, these are the bases of V. Now another one. Think about this. I'm saying that if E1, E2, E3, En are bases of U, fine, and it happens that you try to find Te1, Te2, Ten, and they happen not to be they happen not to be linearly independent, then T can never be 1, 1 and onto image. Then T cannot be 1, 1 and onto image. So these are all some of the important things that you should remember. I'm not getting into isomorphism because that will invoke quotient spaces, and I have not taught you quotient spaces in general. But in general, till this point, you should be able to understand most of the things. Another thing, I'll refer to it that way also, that is coordinate. I somehow forgot to write it. Is that clear? Please let me know in the comment section. Is there any doubt? If there is any doubt, please let me know. If there is no doubt, I'll proceed. So if there is any doubt, please let me know. If there is no doubt, I'll proceed. Okay. I hope it is clear. Let me see. Okay, so let us do some questions and understand whether you have understood this concept or not. Okay, so let us see that if you have understood it or you have not understood it completely. So let us do a few questions. Okay, so let us do a few questions. Okay, so let us see that whether these are isomorphic or not. Okay, let us see whether these are isomorphic or not. So let us say I'm defining a map from R cube to R. I'm defining a map from R cube to R such that T of x comma y comma z is equal to x plus y comma y comma z. Do you think that T is isomorphic? T is an isomorphism, sorry. Do you think that T is an isomorphism? Do you think that T is an isomorphism? So you have this kind of map that is T x comma y comma z. Then do you think that T is an isomorphism? If I define T x comma y comma z as T of x plus y, sorry, this is R cube. But T of x. Please think about this. See, the first thing that you need to check for isomorphism is whether they are 1, 1 or not, right? Whether they are 1, 1 or not. So I'll write it here. First thing that you need to check, so for example, if you don't know, the first thing is you have to check that T is 1, 1 or not. How you used to check in standard 12? You used to take two different things. Let's say x, what I get at x comma, x1 comma, you say x comma y comma z, let us say, and another thing you take x dash y dash z dash. Okay. Now if I take T of x comma y comma z, what do I get? It is equal to x plus y comma z. And if I write T of x dash y dash z dash, what do I get? I get x dash plus y dash comma z dash. What does it imply? If I write T of x comma y comma z is equal to t of x dash comma y dash comma z dash, what do I get? I get x plus y comma z equals to x dash plus y dash comma z dash. What do I get from here? Here I get y is equal to y dash. From here I get z equal to z dash. And if y dash and z dash are equal, then x dash should be equal to x. What does it imply? It implies that if I took this, if I took x comma t of x comma y comma z as t of x dash comma y dash comma z dash, then it implies that x comma y comma z is equals to x dash comma y dash comma z dash. It implies that t is 1 1. It implies t is 1. Now let us say, see, one other thing is very important. See, if t x y is x comma y comma z is related by x plus y comma z, understand that x belongs to R, then x plus y and y also belongs to R, and z belongs to R. Understand? So x plus y will also belongs to R, isn't it? So x plus y also belongs to R, y belongs to R, and z belongs to R. All of these three things belongs to R. It implies what? Overall, the entire thing will be equals to R cube. And what is V? So if I find the range of t would be what? R cube only. Understand, this is from R, this is from R, this is from R. It will take all real values, it will take all the real values, this Z will take all the real values. After all, having taken all the real values, it will be R cube, isn't it? So if it is R cube, that implies the range of t is R cube, and if range of t is R cube, that implies what? That implies that range of t is equal to V. So if you remember, in this particular case, you had this. Let us say that this is U and let's say this is V. So the entire range is equal to the codomain, that is V. So we can say that T is onto as well. Now T is 1 1, T is onto, it implies T is iso. T is an isomorphism. I think it is clear. Okay, so this is one thing. Also, you can say that if I want to write any xyz belongs to R cube. If I want to write any xyz belongs to R cube, all I need to do is take the image of x minus y, comma z. See, if I take the image of x minus y, comma z, what do I get? I'll simply get x minus y plus y, comma z. So I'm going to get x, y, z. Okay, so it belongs to R cube. So if I want to generate any x, y, z, all I need to do is this. And this gives me a freedom of saying that if I want to, since this is my isomorphism, so I can say that 1 1 onto-ness is there. If 1 1 and onto-ness is there, then I can say that my T inverse would be defined. And what is my T inverse? T inverse xyz would be equals to what? X minus y, comma z. So this is how you can define your inverse as well. This is how you can define your inverse as well. I hope it is clear. Now let us do another question. Let us just do a few more questions and not many other. Let us try to see whether this forms a linear this forms a isomorphism or not. R cube to R square, T of x, y, z is equal to x plus y, plus z. X plus y plus z. Does it form a linear? Does it form an isomorphism? So I want to see whether T of x, y, z is equals to x plus y, plus z. Does it form a linear transform? Does it form an isomorphism? Does it form an isomorphism? Does it form an isomorphism? Just think about it. So let us just think other way. Had it been isomorphic, then I know the dimension of, because these are finite dimensions, then dimension of u must be equal to dimension of v, which is not the case. So if we are talking of finite dimensional vector spaces, and U is isomorphic to V, then their dimension should be equal. So if I assume that this is isomorphism, then their dimension should be equal, which is not the case. This is just the first thing that you can see directly. And if you don't want to see this, let us take some counter example. Let us say, let us just prove that, let us prove that T is not 1, 1. If you just prove this, this is going to do every problem. Okay, so I told you that if T is 1, 1, then the kernel of T will only contain a null element. So here the null element is 0, 0, 0. Okay, so if T is 1, 1, then remember I told you that if T is 1, 1, then the kernel can contain only 0, isn't it? It cannot contain another element. So R cube 0 is what? 0, 0, 0, this ordered pair. Now what I want to say from here is, let's say that what x, y, z belongs to R cube can yield me 0. Just think about it. So if I just take 1, minus 1, 1, is it not going to yield me 0, 0? Just think about it. What is 1 minus 1? So it is 1 minus 1 here, and minus 1 plus 1, 0. So it is going to give me 0. It implies what? 1 minus 1 and 1 belongs to what? It belongs to kernel T. Because kernel T is after all what? All elements. Kernel T represents all those elements for which your transformation Tx becomes 0. And here it is. It proves that 1, minus 1, 1 should belong to kernel T. And if you remember, I gave you if and only condition. In fact, I a little bit of sketch the proof as well. So here it is. If T is 1, 1, if and only if kernel T contains a null element. So if it is T is 1, 1, okay, if T is 1, 1, then 1 has to have this thing. So here clearly 1, minus 1, 1, you can say it belongs to the kernel of T, and therefore this is not 1, 1, and hence you can say that this is not isomorphic. This is quite easy to see. I don't think there is an issue till now. So overall, understand in physics, most often we are going to deal with the structures which are isomorphic, because we want to see the similarity. I mean, we want to see the symmetry between the structures. This is why a physicist studies an isomorphism. This is the main motivation of a physicist. For mathematicians, there are enough motivations. Like obviously, their motivation is also symmetry, but understand they would go on doing every bit of you can say thought process. Like we want only some structures. Like we want some structures somehow. So, for example, yesterday I told you one of the things that I told you, and actually I did not. Actually, I used it and I did not use it as it. So actually, I told you that a space, you can say that set of all linear transformation. If you remember, I told you there is a set of all linear transformations as well. So if you remember that I denoted this by this. So it represents what? It represents the set of all linear transformations. And I told you that this happens to be vector space as well. Under the operations of vector addition and scalar multiplication, I referred it yesterday itself. Okay, so set of all linear transformations, they also form a vector space. Okay, they also form a vector space. If you remember yesterday, I told you this. Okay, and I told you that, do you think that this, now today let us think about this. Is it isomorphic to R square? Is it isomorphic to R square? So yesterday I told you that this is a finite dimensional vector space. See, this is a finite dimensional vector space because I told you that if dimension of U is equal to M and dimension of V is equals to N, then dimension of the set of linear transformation which also forms a vector space is nothing but it is equal to M into N. What do you think the dimension of this would be? So dimension of this is 2, dimension of this is 1. This is a finite dimensional space. So dimension of V is equal to 2, and here also dimension of V is equal to 2. Is that clear? Okay, and I told you that if there are finite dimensional vector spaces, I'm saying for specifically for finite dimensional spaces, two structures are isomorphic if and only if their dimensions are equal. So if their dimensions are equal, then they have to be isomorphic. So whatever I have written, the space which has set of all linear transformations from R square to R, it is going to be isomorphic to R square. It is going to be isomorphic to R square. So in fact, writing this is equivalent to saying that you are drawing a Cartesian plane. You're drawing a Cartesian plane. I hope it is clear till now. Okay, so uh, much of these things are more mathematical, not that much physics, but okay, but that's how things are. So to understand all these things are really important. See, yesterday I told you something about Ket and Bragg notation. Okay, Ket and Bragg notation in physics usually we take for quantum mechanics. I told you that Ket and Bragg notations are used for simplifying the things in quantum mechanics, and I told you that Ket notation. Let's say I told you yesterday itself. No? So I told you yesterday that Ket notation that we use. Uh, okay, so Ket notation that we use is generally the Ket contains what? Ket contains generally the elements of Kets are nothing but elements of vector space, and Bra vector contains the elements of the dual space. So there was something called as dual space yesterday that we were discussing. Okay, so understand how did I say this dual space? That for that you'll have to wait till I come to the inner product space. So basically, Hilbert space that we do in quantum mechanics. So Hilbert space is an inner product space. So it is a specialized sort of vector space in which you can define inner product. So, and why do we do so? See, the reason why do we do so, because in quantum mechanics, most often in general, the wave functions represents the psi mod whole square eta represents what? It represents the probability. It represents the integration of psi mod whole square eta represents the probability of finding particles somewhere. Okay, so after all, psi mod whole square eta psi mod whole square represents the probability amplitude. Okay, probability density. So always remember that it has to be equals to 1. So in any case, we want to have such functions which are squarely integrable. If the functions are not squarely integrable, then things won't work. Things won't work. So that is why this Ket and Bragg notation will simplify that particular representation that we do in coordinate space, that is in integral. This Ket and Bragg notation is going to simplify all those things. Okay, so all these things, I know that's not making that sense to you, but I'm just giving you an idea and just putting some seeds in your brain that something why I have written that Bra vector is an element of dual space and Ket is an element of vector space. So for vector space corresponding dual space, the elements of, like for example, I denote this by this and I denote this by this. If you remember, like everybody who does quantum mechanics remembers this. So this is the corresponding Bra vector to this. And how do I say that this would be an element in dual space? For this, you'll have to wait, and you'll have to wait till the inner product. And that then we'll be able to understand. I hope till now everything is clear. So please let me know if there is any dispute, any doubt. Okay. I hope these are very easy things till now. Once we are done with these things, let us do one more question so that try to do this as. So let us define from R cube to R cube a linear transformation. A linear transformation defined by the formula see whether T is an isomorphism or not. Okay, so this is something that I'm leaving up to you. So let us, you just do it as a, let's say, homework, or I'll do it later on. Okay, I'll do it later on. Till then, let us do some other, you can say, let me do some other things for you, otherwise you will not be able to probably do this question. um, okay. Okay, so now let us define a few more things. I think there was one thing that I left yesterday or something. Okay, I left something called as let me do this also first. Before addressing this question, let us do one more thing so that things will become easy for you. Things will become easy for you, and that particular thing you can say um, is called as the uh, I'll write it here. So that particular thing is called as the matrix of linear transformation. So that will help you a lot. Okay, so that will help you a lot in determining all these kind of weird difficult questions at times. So it's not always necessary that in order to check one you're going to do tx1 x2 dash and all those things. So let me just help you with one more thing probably that I left yesterday, and that is called as the matrix of the linear transformation. That is an important concept in your theory of linear transformations. So let us come to the matrix of, and then I'll see this question. Then I'll see this question. Don't worry. Okay, then I'll see this question. So matrix of linear matrix of linear transformation. So this is important thing. So for example, uh, till now we have studied what is linear transformation. Okay, we have studied that if t happens to follow this, and let's say u1 and u2 belongs to u, and t is defined from u to v. If t is a mapping defined from u to v such that this, where alpha 1 and alpha 2 belongs to field f, and this definition is there, we say that t is a linear transformation, isn't it? So this is something that we've done till now. Now if you want to map an ordered basis, a basis to basis, the first thing that comes in mind, that there would be something called as a matrix of linear transformation that will join, uh, you can say, uh, from one basis set to another basis set. If we want to change, there would be something, and an intermediary would come, that is called as the matrix of linear transformation. So intermediary would come. So for example, if I want to relate, I should write in easy language. If I want to relate basis of u with basis of v, how to do that? That is done via matrix of linear transformation. But the one of the most important thing that you should keep in mind is that basis should be ordered. Okay, it should be ordered, and this is the main requirement. You cannot have, yesterday when I wrote actually I messed up with one question now. So actually I replaced like the ordered basis. So if you replace the order, if you do something wrong with the order, then uh, everything will go wrong. So the point is that you should remain. For example, if I'm saying r cube, so in R cube first comes x, then comes y, then comes z. So ordered basis would be 1, 0, 0, then 0, 1, 0, and then 0, 0, 1. This is how you define your ordered basis. I cannot mess up with their order. Is that clear? So I'll write, how should I write? So let me formally write that let u and v be vector spaces over field f, of dimensions, let us keep it general. Let's say n and m respectively. Okay, and let the basis set for ordered basis. I'm writing ordered basis. Ordered basis of u be equals to e1, e2, e3 dash 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 en. Okay, and let's say ordered basis for v is equal to what should I write? Let me write it as f1, f2, f3 dash 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 fm. Okay, so remember this, remember ordered. Please remember, note order. Please keep in mind that order means if I write x comma y, it cannot be equal to y comma x. Here, this thing will not be the same. Okay, please do remember. Okay, uh, so let's say these two are the things. Let's say the ordered basis of u is e1 comma e2 comma e3 dash 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 en, and the ordered basis of b2 is f1 comma f2 comma f3 dash 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 fn. And we want to associate uh, elements of u to v. Okay, so let us say that there is a linear transformation that relates elements of u to v, and what is our purpose? We want to associate a matrix to it. We want to associate a matrix to it. We want to associate a matrix to it. We want to associate a matrix for it. Now see, how would I do so? So one thing is clear. Let's say if I want to write T E1, okay, T E2. If you remember, I told you that if T is a linear transformation, E1, E2, E3, En are the basis of U. E1, E2, E3, En are basis of U. Then uh, these become the what you can say. These become the these are the elements. These are the elements in. I'm not right. These are elements of V. These are the elements of V, right? And I know that see, if E1, E2, E3, En are elements in U, then Te1, Te2, Te3, Ten, these are the elements in V, right? And you know that the ordered basis of V is this. What does it imply? It implies that Te1 can be written in terms of F1, F2, F3, Fm. Te2 can be written in terms of F1, F2, F3, Fm. Tei can be written in terms of F2, F3, F3, F4, Fm. And in fact, Ten can also be written that way. Is that clear? See, one thing you should understand that E1, E2, E3, En, if they are elements in U, then Te1, Te2, Te3, Ti, and Ten are elements in what are elements in V, right? And the standard basis, standard ordered basis for V is F1, F2, F3, Fm. So you can say that all these things, these Te1, Te2, Te3 dash 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 Ten, can be written in terms of F1, F2, F3, Fm. I hope it is clear. If it's not clear, please let me know. So I'll write it as F1, alpha 11 F1, alpha 21 F2 dash 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 alpha M1 Fm. Similarly, I'll write alpha uh, okay, and alpha, I'll write this as okay, and the last one would be okay. So after all, this will become this particular thing. So if I want to relate it in terms of matrices, what will happen? I can say that this T, all these things is equal to some matrix here, and which will be M into N matrix, and here I think it would be F1, F2, F3, Fm. Is that clear or not clear? Please let me know. Okay, is that clear? So what has happened? This particular matrix has converted one basis set, what you can say that if I want to convert from one basis set to another, so this particular matrix comes into the picture. This particular matrix is called as the matrix of linear transformation. Just I'm giving you an idea of it. Okay. Okay, and let's say these are b1s and this is basis set b2. So this particular matrix is often written in this way also. Okay, so what is happening that we are writing b2, we are writing b1 in terms of linear combinations of the b2, right? This is how we are going to do. Is that clear? So elements of b1 are written in the linear combination of b2, right? Is that clear? And in fact, if b1 is equals to b2 is equal to b, then we denote this as simply this. What does it mean? It means that matrix of linear transformation T with respect to the basis set B. I hope it is clear till now. I hope it is clear. Okay, and there is an insistence. There is always an insistence with regard to ordered basis. Why that is an insistence? See, if I want to relate, if I change this order, then this matrix would change. And if matrix would change, then there would be a problem of non-uniqueness. There would be a problem of non-uniqueness. And if I've stated initially that there should be only one and one linear transformation which relates the basis, if you remember initially. So in order to have this uniqueness, we actually insist upon ordered basis. Is that clear? So let us develop the same theory and try to do questions that way. Okay, so let us try to find a little bit of it. Okay, so consider a linear operator. I'm just giving it simple examples first. Consider a linear operator. Consider a linear operator given by t r cube to r square, such that t of x comma y comma z is equals to x comma y simply. So it is again a projection. If you remember, I told you this is a projection of three-dimensional space to a plane basically. So let us define a projection that is t defined from r cube to r square such that t of x comma y comma z is equal to x comma y. We want to obtain the matrix of transformation, linear transformation. We want to obtain the matrix of linear transformation, let's say from r cube to r square. So let's say if the basis set here is b1 and let us say the basis set here is b2, we want to find the matrix of linear transformation b1 b2. So let us do that. If you remember, I have already stated that for r cube the standard basis vectors are 0 comma 1 1 comma 0 comma 0. This is your e1. What is your e2? If you remember, it would be 0 comma 1 comma 0. And what is e3? It is equal to 0 comma 0 comma 1. So these are the standard bases of r cube. What are the standard bases for r square? Ordered way. So if I want to write, I remember I wrote f1. So f1 would be 1 comma 0. And what would be f2? f2 would be 0 comma 1. Now if I take the images of TE1, TE2 and TE3, after all it will belong to what? It would belong to these all elements. This will be belong to r square, this will also belong to r square, this also belongs to r square. So I can say that I can write TE1, TE2, TE3 in terms of the linear combinations of f1 and f2. right? So I'm going to write this. I'm going to write this. What would be T even? T even would be simply, I think, 1 comma 0. What would be TE2? It would be 0 comma 1. And what would be TE3? It would be 0 comma 0. So I can write it as 1 comma F1 plus 0 comma F2. 0 dot F2. This would be 0 dot F1 plus 1 dot F2, and this would be 0 dot F1 plus 0 dot F2. So after all, I can say that what would be my matrix of transformation. I'm just writing it once for your sake. So TE1, TE2, TE3 here. Okay, sorry. We want to write the matrix of transformation. No? So this would be equal to what? Okay. Uh, where is that pen? Okay, sorry. So we want to write the matrix of, sorry. We want to write the matrix of transformation. So matrix of transformation would be what? I'm writing it here. So matrix of transformation T, which relates the basis set B1 to B2, would be simply 1, 0, 0 and 0, 1, 0. Is that clear? Not clear? Please let me know. Is that clear? Not clear? So this is clear here. A two cross three matrix, right? Is that clear? I mean, is everybody following it or not following? Okay, so if I see if anybody is getting a problem, so let's say this is a 2 cross 3 matrix. If I multiply it with F1, F2, what should I say? I hope everybody has got not got. Should I repeat it all over again? I don't know. Is that clear? Should I show it all over again? I think this is clear. Okay, so everybody is saying no. Okay, so I hope it is clear. This particular matrix is called as the matrix of transformation. So this particular thing is called as the matrix of linear transformation that relates B1, B2. If you're not getting it, kindly let me know. I don't know what is the confusion. Nobody's saying yes to it. Okay, so fine. Let's say if nobody has confusion, otherwise, see what you can do. You can check it yourself also. You can check it yourself also. This is very easy to check. It's not that a deal. I hope it is clear till now. Okay, so let us move a little bit. Okay, let us move a little bit further and do a. Actually, if not many people are getting, let me do another question for you so that you will be able to understand what am I doing. So, what should I do? Let me take another example. Okay, let me take another example and let me again tell you this. Okay, so chalo, let me take another thing for you. Okay, so one other thing is that see, understand that. Let me take another basis for this. So let's say. Let me take another basis. See, it's not always necessary now that you have to take the standard basis only. Okay, you can take other bases as well. You can take other bases as well, isn't it? I told you that standard bases are fine, but bases in general you can, like for example, if you want to span the space of R square, then you can use the bases as 1 comma 1 and 1 comma minus 1 also, right? It is not always necessary that you're going to use the standard bases only. Okay, it is not always necessary that you will use the standard bases only. Okay, so let's say what should I do? Okay, let's say I change the basis. Let's say I change the basis for 1. That is, this was the basis set for R cube. If I change this basis to this 1 comma 0 comma 1, 0 comma 2 comma minus 1, and then you have this let's say 1 comma 0 comma 0. This is the basis for R cube, and let us say basis for R square. Let me take it as simple ones. I think 0 comma 1 and 1 comma 0. Now I have messed up with the order and everything. Okay, so mostly I'll use for physics people, I'll mostly use the standard basis only. But let's say if I have changed the basis set, if I change the basis set, what happens? If I change the basis set, then what happens? Okay, let us see that. So if I change the basis set, and now if I want to use the same transformation that I had defined earlier, that t of x comma y comma z is equal to x comma y. Let us take this example only. So that would be equals to t of 1 comma 0 comma 1, which is equal to 1 comma 0. And how you can write 1 comma 0? It can be written as 0 times 0 times, you can say 0 comma 1 plus 1 times 1 comma 0, right? Similarly, you can write t of 0 comma 2 comma minus 1 is equal to what? It is equal to 0 comma 2, which is equal to what? It is equals to 2 times 0 comma 1 plus 0 times 1 comma 0. So, and t of 1 comma 0 comma 0, you can write it as 1 comma 0, which is simply equals to what? Which is simply equals to 0 times 0 comma 1 plus 1 times 1 comma 0. So clearly you can say that t of I think this different basis set b1 comma b2 happens to be what? Happens to be 0 comma 2 comma 0 and 1 comma 0 comma 1. Is that clear? So clearly you can see that with a change of basis would eventually lead to the change in the matrix of linear transformation. It will change the matrix of the linear transformation as well. Okay. Let's say another example. Let us take another example so that you'll be able to understand this thing in better way. So if I want to, let's say, we want to write, let's say I want to write, we want to write uh, the matrix of LT from R cube to R square. And let's say txy comma z, x comma y comma z is given by x plus 2y plus 3z, comma let's say 2x plus 3y plus 4z. Okay, let us take what should I say? Let us take that this r cube is related to r square via this linear transformation. And I want to obtain the matrix. Let us first obtain the linear transformation matrix using the standard basis. I'll write it. Let us first obtain the matrix of linear transformation using the standard basis vectors. Now you see standard basis is what? It is 1 comma 0 comma 0, 0 comma 1 comma 0, and you have 0 comma 0 comma 1. So what would be t of 1 comma 0 comma 0? What would be t of 0 comma 1 comma 0? And what would be t of 0 comma 0 comma 1? What do you think? I think this is easy to find. Please take some time and find it so that we are also able to understand what I'm trying to do. So I'm going to write it directly. So and what would be the standard basis in r square? So I'll write standard basis on r square is 1 comma 0 and 0 comma 1. Okay. So what would be t of 1 comma 0 comma 0? It would be 1 comma 2. It would be 2 comma 3, and it would be 3 comma 4. So if I write this way, what it would be 1 times f1 plus 2 times f2. It would be 2 times f1 plus 3 times f2. It would be 3 times f1 plus 4 times f2, right? So this is how it is going to be. So the matrix of linear transformation T from the standard basis b1 to b2 would be equals to what? It would be equals to 1, 2, 3, and I think 2, 3, 4. Okay, 1, 2, 2, 1, 2, 3, and then I think this is right, 2, 3, 4. Is that clear? Now I'm giving you an assignment. Try to evaluate the same using another basis vectors. Other basis vectors. Let's say I give you those basis vectors so that things would remain easy for you. So let us say I give you a basis vector b dash which is equal to 1 comma 0 comma 0, 0 comma 1 comma 0, and then you have this 1 comma minus 2 comma 1, and you have, let's say, b2 dash which is equivalent to writing 1 comma 2, and you have this 2 comma 3. I'm leaving it to you as a homework. Try to do this. Try to find the matrix of linear transformation. And what you'll find that these two matrices are not equal. These two matrices are not equal. So always remember this thing, that it's not necessary that the with change of the basis you will have the change of the matrix of the linear transformation. Okay, now let us say I give you if I give you a matrix of transformation, that is a matrix of linear transformation, and if I desire what is the linear transformation, if I desire the structure of the linear transformation, that also can be done. Let us do it for the standard basis only. Let us do it for the standard basis only so that things remain easy. Let us do it for the standard basis. So let us describe linear transformation defined from r cube to r square, such r cube to r cube. Let us say for simplicity I'll take r cube to r cube, and let's say the matrix of linear transformation is given by this 1 comma 2 comma 4, and you have this 2 comma 3 comma 1, and you have 3 comma 1 comma 2. Okay, so this is it. So what will happen? I know that t even TE2 and TE3 is equal to what? It is 1 times E1 plus 2 times E2 plus 3 times E3, and then it is uh, 2 times E1 plus 3 times E2 plus 1 times E3, and then you have this T of E3 as 4 times E1 plus 1 times E2, and then you have this 2 times E3. Is that clear? I hope it is clear. Now see, any element in, I'm writing it here, any element R cube, in R cube, that is x comma y comma z, can be written as what? It can, x can be written as x into 1 comma 0 comma 0. Sorry, if I want to write x comma y comma z, I can write x times this plus y times 0 comma 1 comma 0 and z times, and if I want to write it in terms of this, I'll write x e1 plus y e2 plus z e3. Okay, now let us apply this linear transformation T on both sides. So I'll get T x comma y comma z. Here I'll get x into T e1 plus x into y into T e2 plus z into T e3. Okay, and this gives you T x comma y comma z is equals to what? It is equals to x times, what is T e1? This is, I think, e1 plus 2e2 plus 3e3 plus what is this y into 2e1 plus 3e2 plus e3, and then you will have this z 4e1 plus e2 plus 2e3. Now this gives you a freedom here. I'll write it here, T x comma y comma z is equals to what? It is equals to x comma 2y comma 4z x plus 2y plus 4z e1 plus 2x plus 3y plus z e2 plus uh, another one was what? Z1 is 3x plus y plus 2z e3. So what you can say, I told you any t x comma y comma z can be written as x times this, y times this, z times this. So clearly the linear transformation T defined from R cube to R cube, where the matrix of linear transformation is given by this, is nothing but this linear transformation looks like this. So I'll say I'll supply x comma y comma z to you, and you will get x plus 2y plus 4z comma 2x plus 3y plus z comma 3x plus y plus 2z. I think it is clear to you. So this is how you define the matrix of linear transformation. This is how you define the matrices of linear transformation. If that is fine with you, can we do some questions now? Okay, so let us take that question which I left initially, so that that would serve as a motivation to you. Okay, I hope it is clear. If it's not clear, please let me know. That would be good if you let me know, otherwise you'll not be able to get much things now. See, I think this question I have given to you, and I was asking from you that whether this forms a linear transformation or not. Whether this forms an isomorphism or not, right? This is what it was asked here. And I told you, let us do it later. Let us do it later. Okay. See, if you have to see that whether, see, one needs to see when I'm saying isomorphism, what is required. What is required? The requirement is that T, which is the linear transformation, it should be 1 1 as well as onto. And if it is 1 1 onto, then I can straightway say that this would be invertible. And just now, what I have said that if T is related from one basis to another, okay, and we can find that matrix of the transformation, right? If somehow we prove that the matrix of transformation is invertible, if somehow we can prove that the matrix of transition, like linear transformation, is invertible, then we'll be able to say that that T is isomorphic. Then we can say that T is isomorphic, isn't it? Is this something going in your head or not going into your head? So let's say I'll give you an example, and then you probably will be able to understand. See, let's take that example only. Let us take that example only. So let T be defined from R cube to R cube. Let us take this only. Let us say that this be a linear transformation. Let us say this is a linear transformation defined by the formula I think this was the formula, x1 plus 3x2 minus 2x3. You have 2x1 plus 3x2, and you have x2 minus of x3 here. Okay, so now let us try to think about this. Let us try to think. So what I'll do, I'll take standard basis only. Okay, so that will help you. Okay, so let us take of R cube, which is E1, E2, E3. Let us take the standard basis of R cube, which is E1, E2, E3. Okay. Let us try to determine the matrix representation. Let us try to determine the matrix representation. Your even is what? Remember, your even is, so if I write x1 comma x2 comma x3 here in this way, so that it is equals to what? It is said it is equals to x1 plus 3x2 minus 2x3 comma 2x1 plus 3x2 comma x2 minus of x3. This is how it is. Okay. So your T of even, your T of E2, and your T of E3, what it would be? Your T of even is what? It is equals to 1 comma 0 comma 0. So if it is 1 comma 0 comma 0, then you are getting 1 comma 2 comma 0, right? If T of E2 have to write, what I'll get? I will get uh, 0 comma 1 comma 0. So it is going to be 3 comma 3 comma 1. Is that clear? If I want to write T of E3, that would be, I think, minus 2 comma, minus 2 comma 0 comma minus 1, right? And if I want to write it in standard basis, what I'll get? So I'll write it as okay, so what I'll do, so it is 1 times E1 plus 2 times E2 plus 0 times E3. This is 3 times E1 this is plus 3 times E2 plus 1 times E3, and then this is minus 2 times E1, and plus 0 times E2 plus minus 1 times E3, right? This is how you can write. So your matrix of linear transformation T is nothing but it is equal to 1, 3, minus 2, 2, 3, 0, and you have 0, 1, and minus 1. Okay, one needs to see, this is again a homework to you. Try to see whether this T is invertible or not. If this T is invertible, then you can relate this with the x1, x2, x3, and x1, x2, x3 can relate it this in this manner. So you can say that your matrix, your linear transformation is bijective. You can say that if this is invertible, then you can say that the linear transformation T is bijective. And if linear transformation T is bijective, that it implies T is an isomorphism. So from matrix of linear transformation also, you can judge whether your T is isomorphism or not. Okay. Is that clear? Not clear? So are you getting my point? So if I want to generate x1, I can do this. I can go from here to like this particular tuples, and from this particular tuples I can go to this particular tuple provided T is invertible. If T is invertible, then I can do so. If T is invertible, I can do so. And if T is invertible, what does it imply? It implies that your T is being invertible implies T would be 1, 1 on 2, and it implies T must be an isomorphism. T must be an isomorphism. I hope it is clear. Is that clear or not clear? Please let me know. I think this is getting too much difficult for you. I think. So I'm waiting for a minute for people to respond, and then I'll go a little bit more. I think I should go for some easy questions now. Okay, so now let us begin with some different topics so that now you'll get some sort of motivation. Okay, try to do this question now. Simple question, try to do this. I did one question yesterday, the same, almost same question. I'm going to do it for you today so that you feel some sort of motivation. I think there's a lack of motivation right now, so don't worry. These are not that difficult things, okay? If you're going to practice them, you'll not be able to like these are not that difficult. Okay, so chalo, let us do one question. Let us do one question and then you will be able to understand. Okay, so let xy belongs to r square and t x comma y is given by x plus y upon root 2 and y minus x upon root 2. Now if d is a unit disk in the plane, what is the area of the image of d, under this transformation, that is t x comma y is given by x plus y upon root 2 and y minus x upon root 2. If t is a unit disk in the plane, how would you think about the area of tt? Area of tt. And that is clear. See, one thing is clear. If I'm saying of unit disk means what? I'm writing it here. Unit disk means I'm talking about x square plus y square equal to 1. So the area here would be simply pi. Area would be simply pi. Area would be simply pi. Now think about this question. Just think about this question and answer. Probably now you'll be able to answer. Chalo, let me help you out. Let me help you out. See, if this is your space D, let's say this is your space D, where you have a unit disk. So unit disk means what? You have a circle here. You have a, so I'll do it by that only. Okay, so let's say you have a circle here. एक मिनट give me. Okay, so let me take another thing. Okay, I thought I'll be able to do it, but I'm not able to do it. Let us take circle, drag it somehow. Okay, so I have taken a circle here. Okay, I have taken a circle here, and this is a unit circle. This is a unit circle. So this point would be, sorry, this point would be 1 comma 0. This point would be 0 comma 1. This point would be minus 1 comma 0, and this point would be 0 comma minus 1. Now according to our linear transformation, that has been given to us, that t is given to us. What is t? T is given to us as x plus y upon root 2 and y minus x upon root 2. Okay, y minus x upon root 2. So how will these coordinates transforms? If I want to write t of 1 comma 0, it will transform to 1 upon root 2 comma minus 1 upon root 2. How would your t 0 comma 1 transform? Your t 0 comma 1 would transform to 1 upon root 2 comma 1 upon root 2. How would your t 0 comma 1 transform? T 0 comma minus would transform to minus 1 upon root 2 comma minus 1 upon root 2. And how would your t minus 1 comma 0 transform? So t minus 1 comma 0 would be minus 1 upon root 2 comma 1 upon root 2. Is that clear? So basically what will happen? It will go on to transform into C. Square them up and add them up. They are coming as 1 only. So again they will be mapped to a unit circle only. Again they will be mapped to a unit circle only. Again they will be mapped to a unit circle only. See, if you write 1 upon root 2 comma 1 upon root 2, where it would be? So if I write 1 upon root 2, this has transformed somewhere else. So just give me a minute. I'll first draw things. So what is 1 upon root 2? What is 1 upon root 2? So 1 upon root 2 is around 1.707, right? It is around 0.707. uh, okay, it is around 0.707. So if I write 1 upon root 2 comma 1 upon minus 1 upon root 2, so it would be somewhere here. So this is 1 upon root 2 minus 1 upon root 2. Okay, what would be 1 upon root 2? Okay, so this is not even that. This is not even that. Let's see. And this would be this. Okay, and this would be 1 upon root 2 comma 1 upon root 2 would lie here only, right? 1 upon root 2 comma 1 upon root 2 would lie here only. So this is how it is going to transform. Here it would be, okay, so this is not even a circle. uh, Although there's squares, if we add they're coming as one, that is fine, but overall it has transformed into something like this. If I make a close bounded figure here, but then I cannot say that this is right. I mean, I'll have to think upon this. How will it transform? That is a difficult thing to say. What I can do is, I can do one thing. Okay, let me help myself with something like this. Just give me a minute. I think this is not something that I can think of. See how it is transforming. So it's transforming this way. Okay, so I know one thing. This is 1 upon root 2. Sorry, minus 1 upon. So the last coordinate is minus 1 comma minus 1 comma 0 would transform to minus 1 comma 0 transform to, just give me minus 1 comma root 2 comma 1 upon root 2, right? This is fine. This is fine. Okay, and I want to see how, see, one thing is very much clear. If I take this as x dash and if I take this as y dash, it is clear that x dash ka square and y dash ka square is also giving me 1 only, right? So I cannot expect a square out of it. I cannot expect a square out of it. So it is obviously going to be what you can say. So this is how it was now. So it is, this is the linear transformation, right? So if you apply t x t uh, uh, x comma y, you are getting this, right? Okay, and even if I square them up, so let's say this is your x dash and let's say this is your y dash. Okay, so clearly I can write that this is x dash square plus y dash square. This I'll get x plus y upon root 2 whole square plus y minus x upon root 2 whole square. Okay, this, so we are getting here x square upon 2 plus x square upon 2, okay, plus y square. Okay, and it was equal to 1. It was equal to 1. Okay, it was equal to 1. Okay, clear. Okay, so here also we are getting the same thing. Here also we are getting the same thing. So here also, so I can say, so TD in with the TD, see what TD is here. So TD is here, x dash is equal to what? It is x plus y upon root 2, right? And what is y dash? Y dash is simply y minus x upon root 2. Okay, if I square them up and add, what am I going to get? I'm only going to get 1 only. So after all, this is also a unit circle. So what I can say, the area would be pi into 1. The area would be pi into 1. This is simple. I think the area should come as pi only. Let me check. Area should come as pi. Okay, area is pi. Good. So I think this is clear. I think I got just confused because of this transfer. Overall, understand. So understand that this TD is nothing but it is equals to what? It is equals to x plus y upon root 2 into and y minus x upon root 2. And if I square them up and add, what am I going to get? I'm going to get x dash ka square plus y dash ka square equals to 1. So after all, this is also a unit circle only there. So if that's a unit circle there, you know that the area of unit circle is what? It is simply equals to pi. it is simply equals to pi. Is that clear? Not clear? Okay, so I hope this is quite clear to you, and if this is not clear, please let me know in the comments. Okay, so now let us go a little bit further and try to see a few more things. So see, if the same thing was given to me, what one more thing I could have done, I could have related the standard basis of this, let's say D, the standard basis of D, because it is in two dimensions, it would be 1 comma 0 and 0 comma 1. What would be T, the linear matrix of linear transformation? This is, if I want to write 1 comma 0, T of 1 comma 0, I'll get what? I'll get 1 upon root 2 comma minus 1 upon root 2. And what would be T of 0 comma 1? T of 0 comma 1 would be 1 upon root 2 comma 1 upon root 2. So I can write T of 1 comma 0 as 1 upon root 2 E1 minus 1 upon root 2 E2, and I can write T of 0 comma 1 as 1 upon root 2 E1 plus 1 upon root 2 E2. So the matrix of transformation T would be equals to 1 upon root 2, 1 upon root 2, and minus 1 upon root 2 and 1 upon root 2. Okay, so always remember, if here it is D, it is related with the transformation T, and here is something, let's say something. If I want to find the area, so always remember the area of TD is equals to this determinant times area of D. Remember, the area of D was simply 1. It was simply pi. And what is the determinant? This is 1 by 2 minus 1 by 2. Plus 1 by 2. This is 1. So you can get area from here as well. This is equals to pi. Okay, so from here also you can get the area. So what you need to do, just find the matrix of linear transformation, try to take the determinant, multiply it with the area of the D, then you will get the area of TT. This is quite easy to see. I mean, this is how you can do it. Very fastly. So let's say I'm giving you just an example. Let us say if I give you this question, let theta belongs to 0 to 2 pi, and let T be equals to what? Let T be equals to cos theta minus sin theta, and cos theta. And if I say that B is a closed unit disk. Closed unit disk means what? I'll write, this is quite mathematical right now. So this is x square plus y square equal to 1 I am referring to. I want to write what is the area of TB. So remember, the determinant of this is 1. Remember, this is an orthogonal matrix. So determinant is 1. 1 into the area of B. 1 into area of B is pi. So answer is pi. Finished. So you don't have to see how it's going to transform and all those things that I did, that I was doing. Is that clear or not clear? I hope it is very much clear to you now what I want to suggest. I mean, these are not that difficult question. So I hope to meet you tomorrow, and we'll do dual basis, and probably we'll enter into the quantum mechanics part from tomorrow itself. So I hope you're liking whatever I'm teaching, and if there is any doubt, please let me know. I don't think that all these things are not going to get related. Once in a while, when you're going to get into the operator theory, all of these things are going to come back, and that's how you're going to relate it. So with this, I'm ending this lecture. I hope to meet you tomorrow in numbers, and take care. Bye bye.